Okay, guys, welcome. Today we're going to talk about the real number system. So we're going to talk about some basic introductory concepts that will allow us to define some things that we'll need for use later on in the course. And we're really going to sort of lay the foundation in this first chapter as a whole, but very specifically in this first video. So the first topic that I want to discuss is the idea of what we mean by a set. Okay, now a set is just any collection of objects or numbers, and each of those things we would call an element or a member of the set, right? So for example, here we have an example where we have this set A, and it contains the numbers 4, 5, and 6, right? So anytime you have a set, a lot of times we use a capital letter to denote a set. So A represents a set here. And then if we want to talk about the elements that are inside a set, we usually use these curly brackets and then just list the elements in the set and then close it with the curly brackets as well. Right? So this statement here just tells us that A consists of the numbers 4, 5, and 6, of course. Now, a lot of times you'll also see something like 4 and then this funny little E sort of character there, and then A, right? And this character here, this is the Greek letter epsilon. And what this really means is that it either belongs to A or is an element of A, we could also say. All right, so that's what we mean by seeing that, okay? Now, just to see sort of a quick example, let's look at the following. So if every member of a set A is also a member of set B, then we say that A is a subset of B, right? So for example, if we look at two sets here, we're going to say that one set is the set of LaSalle students, and another set is the set of college students in Philadelphia, right? Well, since every LaSalle student is also a college student in Philadelphia, if I were to call this first set, if I were to call the LaSalle students set A and the college students in Philadelphia set B, then in this case we would say that A is a subset of B, right? And a lot of times we actually write this with sort of like a curly C there, right? So you could say that if you wanted to say is a subset of, you could also use this little C character here, right? And so this is written either like this, or sometimes there's also a line under it as well. All right. Okay, so let's look at another example involving sets. So here we're going to talk about the set C, which consists of all names of the names of all the coins whose denomination is less than 50 cents. So in part A, we actually want to write out what C is in set notation, right? So, and all we mean by set notation is to use the curly brackets. Well, we just want to go through and we want to think of all of the coins whose value is worth less than 50 cents. So of course the first one is the penny, because that's just 1 cent. We could also go nickel. We could use dime. And then of course we could have the quarter. Now, since this set just wants coins who are strictly less than 50 cents, we don't want to include a $50 here, right? So those are going to be our elements belonging to our set. All right. Now in part B, they want to know Is a dime an element of C? And of course, yes, because there it is, right? And of course, it's less than 50 cents, so it's right there. All right, now I sort of gave away the answer for C a second ago. We want to know, is a $half in C? And of course, this answer is no, because it's not less than 50 cents. It is 50 cents, right? So that's different. All right, and then last but not least, in part D, we're now going to look at the set H, which is the nickel and dime. And we want to know, is that a subset of C? And of course, the answer is yes, because the nickel is in C, and so is the dime. So both are in C. So H is a subset of C. All right. So that's sort of the idea behind sets here. All right. Now, the other main topic that I want to look at in this video is the type of numbers that you can find in the real number system, right? So the first type of number that we could talk about is what's called the natural numbers, right? And this is just any number that you would use to count things, right? So for example, if you're counting things, you don't start at 0, and you don't use fractions, and you don't use negative numbers. So this is just all your, one way you can think of this is that these are all positive whole numbers. Right? So starting at 1, then the next one 2, then the next one 3, 4, 5, so on and so forth. And those dots just indicate that it goes on forever, while repeating the same pattern. So of course you have 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to, you could keep going towards infinity. All right. The next one is the integers, which includes all of your natural numbers from before, but you also pick up 0, and you also pick up the negative whole numbers, right? So if you look at this part here, if you look at 1, 2, ... those are all your natural numbers, but you also pick up 0, and you also pick up all of these negative whole numbers as well, right? So these are all, basically you can think of them as whole numbers and 0. And we can say whole numbers plus or minus and 0. Right? Now the next one is what's called the rational numbers, right? And if you're looking at a rational number, that simply means that you have a number that you can write as a fraction, right? So these are fractions, where each number in the top and the bottom is a whole number, right? So top and bottom number are both whole numbers. Right, so that's key there. You couldn't have like pi over 2 or something like that, and we'll get to that in a second. All right, now the next one is a little bit misleading, because we're going to talk about the irrational numbers, and it says that they're numbers that cannot be written as a fraction. Now, when I mean written as a fraction, I really should include that where the top and bottom are whole numbers. Right. So what type of these numbers have you seen before? Well, the most common example that we use for irrational numbers is pi. Right. We'll talk about more as the course goes on, but really, if you're looking at a rational number, it's usually something weird like pi, or like a square root of a number, like square root of 2 would be another irrational number. And of course, a real number includes all of these. And really what you need to know about real numbers is that there are no imaginary parts. So there's no i's in these. Right, now, if you don't have no idea what I'm talking about in terms of imaginary numbers or i's, don't worry about it. We're going to get to that later on in the course. All right, but these are just all different types of real numbers. Okay, now another helpful way to classify rational and irrational numbers is given by the following. So if you have a rational number, if you were to write it in decimal form, you're either going to get a decimal that stops, or you're going to get some kind of a pattern, some kind of a repeating pattern, right? So for example, if you look at a rational number like 1/3, if you were to write that in decimal form, you're going to get 0.3333, and that's just going to repeat forever. Now, since you get that repeating pattern, that of course is going to signify that you have a rational number, right? Another example would be like 1/2. And of course, if you write that in decimal form, you get 0.5, and of course that just stops, right? So that's another example of a rational number. Now, for example, if you look at pi, that of course is like 3.1459, and it goes on forever, and there's no pattern and there's no sort of repeating nature, so there's no repeating pattern. So that is going to be your telltale sign that this is, of course, an irrational number. Right? Now, of course, we can hopefully maybe notice some things about this a little bit before, but the real numbers can be thought of sort of in this box diagram here, right? Now, we said that we had the natural numbers first, right? Those are all of our numbers that we count with. Now, you pick up in this diagram, they sort of consider integers and whole numbers as being separate, but the natural numbers, the important thing here is that the natural numbers are contained inside of the integers. It's not really a good color to use, right? So the natural numbers are included in the set of integers, right? Now, of course, all of the integers are included in the rational numbers, because if you wanted to write an integer as a fraction, you would just write it over 1, right? So any integer is also a rational number because you can also write it as a fraction. All right, but if you look off to the side here, irrational numbers are sort of on their own, right? So irrational numbers are completely different from the other three sets, but all of these all of these different sets of numbers make up the real numbers. Okay. All right, so just as a quick example, let's go through these right here. We want to basically say, what are each of these numbers? Are they rational? Are they natural? Are they real? Are they integer? Are they irrational? All right, and we want to basically include every single one that we can. All right, now if we look at -3, it's not a natural number because it's negative, right? But it is an integer. All right, it's also rational because I could write it over 1 if I wanted to. And of course, it's also a real number. Of course, now the most specific we can get is an integer, but don't lose sight of the fact that it is also still a rational number and it's a real number. All right, let's look at part B. All right, now you have 0.8. If you wanted to, you could write this as a fraction. You could write it as, since it's in the tenths column, you could write it as 8/10 and then simplify it, and you'd see that you have a fraction there. All right, but right away you see that this is just a decimal that stops. So this is a rational number. And of course, once it's rational, it's also a real number. And again, the way that we would probably consider this to be most specifically is we would say this is rational. All right, but again, also still a real number. Now part C, I don't know why that printed like that, but I wanted to look at pi. And of course, this is what we've talked about already a little bit before, but pi is usually the most common example of an irrational number. And of course, it's also a real number. Okay, and of course, part D, we have -4/5. And of course, that is a rational number. And once it's rational, it's also real. And of course, the most specific, again, we can get is that it's rational. Now, we've said that all of these are real. So I just want to give a quick example of a non-real number or a complex number that is not real. Would be something like 3 plus 2i, right? So of course, this, again, if you haven't seen this before, don't worry about this just yet. We'll get to that later on, but if you see an I in it, that's your red flag that it's no longer a real number. Okay, now the last thing I want to discuss in this video is just the concept of a real number line, which we will use frequently throughout the course. But if we want to draw a number line, and we'll plot these points on here, right? We just draw a horizontal arrow. And usually it's helpful to just indicate where 0 is, right? 0 is sort of the center of your number line, right? And of course, to the right, you have positive numbers. And to the left, you have negative numbers. And of course, the further away you get from 0, the more positive or more negative your numbers are going to become, all right? Now, at first, most students like to just plot some sort of natural numbers in the order. We could also put some of the negative versions of these. And then, of course, we're just going to fill in our following points that we want. Now, if we look at -3/2, it might be helpful to think of this in decimal form. So if we convert -3/2 into a mixed number, how many times is 2 going to 3? We have 1 with 1/2 left over. And of course, it's still negative, right? So -1.5 is going to be between -1 and -2. All right, now the next one's a little easier. We have just 2, right, which is just 2. And of course, that's already marked on here, so that's just right here. And of course, last but not least, if we look at 13/4, again, this is probably helpful to convert to a mixed number. So how many times does 4 go into 13? That'll go in 3 times with 1 left over. Right, so that's 3 and then a little bit more. So that one is going to be right about here. So, all right, so that concludes this video on the introduction to the real number system. I hope you enjoyed, and I will see you next time.